Hi everyone. Before we start, let me tell you that I have I posted my feedback on your proposals. So please take a look at that. Each team has individual feedback. Also, I have mentioned the global feedback. So take into account both individual feedback and global feedback. I don't know why some teams haven't seen my individual feedback. Because when you read it, it tells me that you have read it. Some teams haven't, so please check my feedback. If you are in both courses, I have done it in both courses. Just see my feedback, individual feedback also, as well as the global feedback for your proposals. So that's if you have also statistical machine learning, the day after tomorrow is also the midterm exam for that. The midterm exam for deep learning is next week. Okay, so yeah, and also for midterm, don't restrict yourselves to the questions of assignment, although I will try to make the exam similar to the assignment, but we'll have some other questions. For example, one question which comes to my mind, I will probably include that, is convolution. The convolution operator. It's very easy question, right? So we have an image and a convolution filter. Just apply convolution. So I'm saying that study other parts which haven't appeared in the assignment too. And as I said, the exam will be open book. And yes, next week, please bring your devices, because you will download the questions and the PDF of questions, and then you will answer on the sheets, and I will collect the sheets and I will probably give them to TA, but it's also good for the sake of reference. Just take a picture and also upload to course link. Okay, this is what we are gonna do. So any question? No? Yes. About the assignment question. Okay, question 3. Yes. The what? The signum you should use, right?
So for the gradients are 0, right?
But I said there is formula for perceptron update. Do you remember? The what? OI. What is OI? Summation of WI XI. Where is WI? I gave you the initial weights. So WI, you have that at every iteration. So initial weights you have, W gets updated for the next iteration. Also, you have W's. Therefore, you have OIs. Then you pass it through the signum. And for the formula, I think it was here. It's here. This is the formula, right?
Can we use the equation? I think it's 15, the same as well.
The equation?
15, the same value.
15.
Because I think they're supposed to be the same, but the difference, because there is just one end, one eta, the other one's 2 eta, so I don't think there's.
I understand. Okay. First off, in this formula, I think one of Sam's questions was this. So we have 2 eta here, which is missing. So that's one thing. The one question that someone here asked is that here in equation 15, we also derived the thing, but it has eta. These slides, I was saying that you can derive that formula using, this is the proof of that formula, yeah. But try to use that, because in my solution key, I have used this formula, okay? Questions 7 and 8. No, the gradient descent, you can prove these equations by gradient descent as we did, right? But you should use the formula. The formula can be derived by gradient descent, but this is perceptron. This that I said. I asked you whenever I asked you to use an algorithm, use that algorithm. I didn't say use gradient descent. I said use perceptron training. Okay. So if I ask you use other line training, then you need to use other line training. So yeah, gradient descent. You can derive these equations as we did using gradient descent too. So any other question? No. By the way, hi. For GAN, as I said, you use also another variant. Yeah. Okay. So, so that's one thing. Okay. Before we continue, so what we talked about transformer last session. Now, now we are continue with that, going to BERT and GPT. But before that, I tell you one mistake which I made last session. So do you remember this slide? I said for multi-head attention, we are stacking the attentions like this. Do you remember I said this? It's not like that. Sorry about that. So the multi-head attention applies attention several times for each times rather than stacking them through each other. So I think it was obvious in the next slide, which you saw. As you see, we are applying. So after these linear transformations, we have h of v's, h of keys, h of h values, h keys, and h queries, right? And then we concatenate them. So it doesn't mean that they come back to back. So applying attention h times, that wasn't a stack of attentions. That's one thing, and we hope that it finds. Because do you remember in convolution, for example, we had several filter channels, and each filter was playing some role and finding some features. So if you apply several attention several times, each attention will play some role or take some responsibility. One attention, it gets the attention of pairs. One attention gets the attention of pairs of pairs. One attention gets attention of pairs of pairs of pairs. So that's how it works. When some feature is extracted by some attention, it's not extracted by the other attention because it will be redundant. That's the thing. And why did I make that mistake? Because somewhere we have some stack, and where is that? This is here when we have n times. Do you remember? I said n times this is repeated. This is a stack. So it means that we have this, and then again this, again this, right? So this is a stack. Okay, we talked about transformer. I'm not going through that again because I don't have enough time, because we already talked about it in the previous session. Now let's continue with the complexity of attention. So attention is all we need. What do we say? The output of decoder is fed to the masked multi-head attention module of decoder with some shift. We saw that. And this is not a notion of recurrence. Okay, because in recurrence, we do recall what we had in recurrent neural network. So we don't have that here. Hence, there is no any recurrent module, and the only thing which we use is attention. So attention is all we need to learn the sequence, and there is no need to any recurrence module. And it was a breakthrough in natural language processing. Nowadays, the state-of-the-art NLP methods, even some of the state-of-the-art computer vision methods are using transformers and attention. Okay, complexity comparison. In self-attention, we learn, what do we do in self-attention? We learn the attention between the words, right? We learn attention of every word to every other word in the sequence of n words. Assume we have n words in the sequence, right? Then also, what do? We learn a p-dimensional embedding for every word, right? We learn a p-dimensional embedding for every word. Therefore, its complexity becomes O(n squared p). Because for every word, we are attending to every other word. So this gives me n squared. And we also have n words for each of which we are learning a p-dimensional embedding space. So that complexity per layer is O(n squared p). However, in recurrent neural network, it can be proved that the complexity is O(n) p squared. Okay, this is one difference. So we have mentioned them here in this table. Although the complexity per layer in self-attention is worse. Why? Why is O(n) squared p worse than O(n) p squared? Because usually n is large and p is small. The embedding, the dimensionality of embedding is small, but n is the number of words in the sequence. So it's the complexity of attention is worse. But why do we say that attention is awesome? Because it can be done in parallel, right? Because all the words of sequence are processed simultaneously, right? Because for attention of a word to another word, do I care for another pair? No, I can calculate the attention in attentional pairs of words in parallel. So O(n) squared p can be done in parallel, and it's not very bad. However, in recurrence, we'd have to be sequential, right? So that's one thing. Another thing is that, so for sequential operations also, we process in attention, we process the n words simultaneously. So its complexity is O(1), but in recurrence, we do them sequentially. So it's O(n). It's worse. So in recurrent neural network, in terms of sequential operations, it's worse. And in terms of maximum path length, also attention wins over recurrent neural network. Why? Because attention, we learn attention between every two words, right? So maximum path length between the words in the sequence is O(1). You always have relation between every two words, right, in the sequence. So it's O(1). But in the recurrent neural network, when we say big O notation, it's the worst case. What is the worst case? One word is at the start of the sequence, one word is at the end of the sequence. So it's O(n). The relation of the first word and the last word is O(n), because you need to pass through every single word to reach to the other one. It will be O(n). So as you see, in general, by comparison, we saw that attention in terms of complexity is better than recurrent neural network and LSTM. Okay, now let's talk about BERT. So BERT is short for what? Bidirectional encoder representations from transformers. Okay, it's short for this, and we'll see why we name it like this. So what is it? It's simply a stack of encoders of transformer. Do you remember? Transformer was an autoencoder, having an encoder and decoder, right? So BERT throws away the decoder and says only encoder suffices for me. And then, but encoder doesn't have enough parameters to learn for me. Let's increase the number of parameters by what? By increasing n, the stack of, do you remember we had n times the stack? So increase n in BERT. This is what they have done. In other words, so we have transformer encoder blocks. Although some NLP methods such as XLNet have slightly outperformed it, but BERT is still one of the best models for different NLP tasks, such as question answering, natural language understanding, sentiment analysis, language inference. All of these are tasks in natural language processing, and BERT is used a lot, especially in industry. They use BERT a lot, okay, for these tasks. In phones, phone companies use BERT, okay. So BERT uses a technique of masked language modeling. So what do I mean by masked language modeling? This is a task in NLP. You give me a sequence, you mask one of the words. So one word in the middle is missing somewhere in the sequence. And then from the other words in the sequence, I predict what word it is, okay? That's called masked language modeling. And what do? They, for training, they mask 15% of the words in the input document. Also, the input document in NLP is also called corpus, okay, corpus. So, for example, their corpus might be the whole Wikipedia, for example, right? So the corpus might be the internet data. So from the corpus, they mask 15% of the words randomly. And then they ask the model to predict the missing word. Okay, and this missing word might be at the start, at the middle, at the end of the sentence, doesn't matter. And a sentence with a missing word is given to every transformer encoding block in the stack, right? And it is supposed to predict the missing word. So what do they do? For example, this is BERT, a stack of encoders. We have transformer encoders. And for example, I have the sentence Leonardo da Vinci is a portrait by, Mona Lisa is a portrait by Leonardo da Vinci. So for I mask this one and this word and this word. I give each of these to a transformer encoder, and it should predict the correct word for me. This is what they do. Okay, so they have, they have labels. Why? You can see it as a self-supervised learning algorithm. What do I mean by self-supervised learning? First off, self-supervised learning prepares the labels itself. You don't need to give the labels to them. If you needed to give the labels to the machine learning model, that would be a supervised algorithm. If you didn't use labels at all, that would be unsupervised algorithm. But we have self-supervised learning, and that means that the model needs labels, but it generates the labels by itself. Okay, this is what's and the BERT is self-supervised learning. Why? It takes some sentence and it masks one of the words, but the word that it has masked, it knows what it was, right? So because of this simple idea that they could generate labels automatically, they were able to use the whole internet data. So because labeling is time-consuming, resource-consuming, people don't want to label in a way, so they make it automatically. In this way, their hands are open to use the whole internet data. And so they had a huge text data of internet. And by the way, so BERT is bidirectional. What do we mean? Because it's, for example, this is a sentence and this is a word. This is the next words in the sentence, right? This is the masked word. As you see, it sees beforehand, and also it sees afterwards. So the words before, which have come beforehand the word, and also the words which have come after the word, right? So it sees them, conditioned on them, it predicts the word. So it's not a causal model. Okay. Once I had an interview in industry. This was one of the questions. Is BERT a causal model? No, it's not. Okay. However, GPT is a causal model. What do I mean by causal? Because it needs its future, right? Needs its future words. And why is it able to be bidirectional? For being able to be bidirectional, it needs the future words, and we have the future words in the sentences for training. However, it should also use the future words for being bidirectional, but it is using. Can you tell me why? It is using both the previous words and the future words. It's using them. Where? What was BERT? A stack of encoders of transformer. In encoder of transformer, what did we have? We had multi-head attention, self-attention, right? By self-attention, I mean I use the attention of a word with the words within its own sequence. And we didn't have any mask for the future words in encoder. In decoder, we had. Do you remember? Recall transformer. Do you remember? This is an important thing for you to understand. This was encoder, right? And we had multi-head attention here. Multi-head attention was using both future words and the words before the word. So it was considering the attention of every word with the previous words and words that come in afterwards. And that's the reason. That's the reason exactly, because we have multi-head attention and it's not masked for the future words. However, in decoder, do you remember this? We had masked multi-head attention, right? And what was this masking doing? Here, we had it. Do you remember? What was this mask doing? It was saying that I masked the future words. Why? Because I don't have the future words yet in decoder. Remember? I don't have the future words yet. Why? Because they're coming from the outputs of the decoder, right? And the words are being generated one by one. So I don't have the future words. Therefore, in decoder, I don't have the future words. But in encoder, I have them. Therefore, in decoder, we use masked multi-attention. But in encoder, we only use multi-attention. So in decoder, we don't have the future words. We are only conditioning on the previous words. But in encoder, we are conditioning on both previous words and words afterwards. This means that encoder is not causal, but decoder is causal, right? BERT is a stack of encoders of transformer. So it can be bidirectional. GPT is a stack of decoders of autoencoder. So it only conditions on its previous words. So it's a causal model. BERT is a non-causal model. GPT is a causal model. Okay. Did you get it? And now I think you understand why they call it bidirectional. B in BERT is for bidirectional. Did you get it? Did you get what I said? BERT is bidirectional. GPT is not bidirectional. Because BERT has multi-attention, which attends every word to its previous and afterwards, right? However, GPT only conditions on its previous words. So GPT is not bidirectional. Okay. So basically their training is different. For training in BERT, we mask a word in the middle of the sequence and we have the words before and after. However, in GPT, it can't be done. Okay, so as I said, it's bidirectional. It jointly conditions on both left and right context of the word. And it is for the same reason that we are attending every word to the previous words and words after. It's a context-aware embedding. And compared to the embeddings which are not context-aware, it's better. Why? For example, word-to-vec is an NLP algorithm which is not context-aware. And as I told you once, an example. So consider the word bank. There is a lot of two sentences. There is a lot of vegetation in the bank of the river, and money is the bank. Money is in the bank. Bank is the same word, but used in two different meanings, right? But word-to-vec has one embedding for the word bank. So that's a flaw of non-context-aware embeddings, such as word-to-vec. But BERT is context-aware. So it sees the other words in the sentence. For example, in the sentence bank, there's a lot of vegetation in the bank of the river. It sees the river vegetation, so it knows what bank here means. Okay, so we have different BERT embeddings in various sentences. Interesting, right? So that's one thing, an example, and these are the examples which I mentioned. And it also outputs an embedding. So in addition to having an embedding for every word, it also has an embedding for the whole sentence. If you see its code, you'll see that it also gives you an embedding for the whole sentence, the network. So it has, in addition to the embedding for the word, it has one output for the whole sentence. Okay, how is it useful? These are practical uses that I'm saying. These are not theory. In industry, for example, you want to do spam detection, right? So you give the sentences to the BERT and it gives you some embedding. It's not it's not perfect, but it works well. Then it gives you some embeddings for the sentences. Then you simply train a simple classifier afterwards in order to find out whether it's a spam or not, right? Because you have labels, you have some training data, you know that these sentences are spam, these sentences are not spam. So you pass them through the BERT, it gives you some embeddings for the sentences, and then you train some simple classifier afterwards for finding out whether it is spam or not. And that classifier might be a simple classifier such as support vector machines, SVM or something, or one layer of neural network. For example, you have BERT, you add one layer of neural network at the end, okay? Then you do transfer learning. Do you follow what I'm saying? No? Wherever you didn't understand any part, please let me know so I explain. Okay, so here we have BERT. I give sentences to it one by one. It gives me some embeddings. I call them X tilde. Okay, so these are X and it gives me some X tilde for every sentence, right? Then I want to train some spam detection. So what do I do? Spam classification. So then I train, for example, an SVM for saying whether it's yes or no, whether it's a spam or it's regular sentence. So far clear? We have the labels. So I know I have for X, I have some labels. And labels are 1 or -1. Either they are spams or not. Okay, so I think it's clear for you, right? So simply, this BERT is just a kind of feature extraction. It's extracting the features for my sentences, right? And I have some classifier. However, I can replace this classifier with one or several layers of neural network. What do? I have BERT. I just add several layers or one layer of neural network. And this is one neuron with sigmoid activation function. What does it give you? Some value between 0 and 1 by threshold half. You find out whether it's yes or no, spam or not. Clear? Here in the embedding layer, I have X tilde. Right? Okay, now 2 ways to train this layer. This or several, either one layer or several layers. How? You should do transfer learning. How do we do that? We have some loss function. For example, here, what is our loss? Cross entropy. Why? Because it's a classification problem, right? I use cross entropy loss function, and then I do back propagation in order to train this layer. There are 2 ways to do that. Either, so I initialize the weights of BERT by the weights of BERT which are available in the internet. Why? Because I shouldn't train BERT from scratch. They have trained it for months on the whole internet data, right? I shouldn't train BERT from scratch. I don't have the servers and these things. So for initial weights, rather than random initialization, I use the weights of BERT in the internet, which is available in the internet, GitHub or whatever. And then usually they put it in S3 AWS servers, right? So you download them and then you have the weights and then you use them. Okay, however, there are 2 ways. Either you train the whole thing. What does it do? Train the whole network. So it trains this layer. Also, it fine-tunes BERT. Fine-tunes BERT. Or you freeze it. You say, I freeze the weights of BERT. I don't want to change the weights of BERT. So my embedding will be always the same as BERT's embedding, but I only want to learn this layer. As I said, transfer learning can be done in 2 ways. Either you freeze the weights, initial weights that you had, original weights, and you just learn the last layers, or you train the whole thing, which fine-tunes the original weights. Okay. So there are a lot of things you can do. As you see, it's very interesting. Cool. So also, yeah, as I said, we can do transfer learning by add one or several neural network layers. Okay, now let's go into the settings of BERT. What does it do? It has 6 encoder layers. Okay, then 512 hidden layer units in the fully connected network, and 8 attention heads. So do you remember H? So for BERT, they have used 8 attention heads in multi-head self-attention module. Also, so by the way, this was in Transformer, I apologize. But in BERT, they have used 24 encoder layers, 124 hidden layer units in the fully connected network, and 16 attention heads. So now compare these two. They have increased all of the parameters. right? Why do they do that? Because they know that they have servers, they have a lot of data. Let's increase the parameters. If we don't have enough data, and if we don't train enough, by increasing the parameters, you just overfit. But they know that they won't overfit because they have enough data. And also BERT, which is a large BERT. Usually the default BERT is a large BERT, and it has a lot of parameters. However, in industry, you don't have enough memory and these things, right? You will have memory error and these things, especially when we are doing it in embedded systems, such as phone and these things. So they have trained smaller versions, small BERT, tiny BERT, distill BERT, Roberta BERT. All of these are small versions of BERT that you can use in your embedded systems. Assume you go to industry. So in addition to theory, I'm teaching you practice too. You go to industry, you have a startup, right? You need your startup trains machine learning algorithms for embedded systems for phones. You can't use BERT. It doesn't fit in the memory of your phone. You have to use the smaller versions. And how do they train these smaller versions? Can you tell me? So there are some techniques for network compression. If we have time in this course, I will cover them. So what do they do? One of the good techniques is knowledge distillation. Knowledge distillation, hence the name distill BERT. Distills knowledge from the large network to the small network. Its idea is very simple. It's very simple. So you have the large BERT here, and you call it teacher network. Teacher network. You have the small BERT. You call it a student network. Okay. Large BERT, you either have it from the initial ways or you train it. So there are several ways. You can train these simultaneously, or you already have the student network trained. Okay. Then it tries, the small BERT, the student network tries to mimic teacher network. Right? It has a smaller number of parameters, but for mimicking the output of large BERT, it has to learn how it is working. It will not become as perfect as large BERT, but it will be good enough. Okay. And its last functions are easy. You don't need to worry. I think if we have time, I will cover it. But the idea is this: just have a smaller version of network. It mimics the larger network. Okay, and that's called knowledge distillation. There are several techniques for doing that. Okay, and we also have BERT for medical text. For example, assume you have some medical images. The caption is saying that the doctor has said it is a tumorous histopathological patch or whatever. So you have medical text, and for that they have trained it by it's called clinical BERT, bio BERT for medical texts. So they have used BERT and they have fine-tuned them for the medical text. Okay, GPT. So GPT is short for generative pre-trained transformer. Okay, and the first one was GPT-1. Okay, it was another state-of-the-art method for NLP. So they were competitors, GPT and BERT, but they have different tasks. I will tell you. So it's a stack of decoders of transformer. So it is built using transformer decoder blocks. And what do we have? In GPT, we have multi-head attention with cross attention. Do you remember? In transformer, we had that in the decoder of transformer. Let's go back to the decoder of transformer. Do you remember this decoder of transformer? Here, we had what? Masked multi-head attention. Do you remember? We also have multi-head attention, right? So this multi-head attention, the second one, which has query and values from the output of encoder. Recall these two arrows. Where do they come from? The output of encoder. I don't know if you have seen my previous lecture or not. Were you in the lecture? If you were, you remember what I was saying that I have erased here. So here, this is the full transformer. I want to show you the full transformer. Okay, this is a full transformer, right? This multi-head attention gets the queries and values from the output of encoder. However, the keys and the queries and keys, but the values come from the decoder, right? GPT is only decoder, a stack of decoders. So it gets rid of, throws away the encoder. So we don't have any encoder. What happens? Where do these come from? Assume you were a software engineer in OpenAI. You were coding this idea several years ago. We were coding that. And we said, okay, BERT had a stack of encoders. Let us do this. Let us implement a stack of decoders, right? This is we are now in the shoes of software engineers in OpenAI. So, okay, we code it, but there is a philosophical question. Where do these come from? I don't have any encoder. So the simplest the simplest solution for a problem is what? Erasing the problem. So let's throw away this module, right? Let's throw away this module. This is exactly what OpenAI did. Okay. Let's go back to where we were. Always put yourself in the shoes of software engineers in big companies, and you'll see how they have thought when they were coding. Okay. So let me come back to where we were. Okay. So as I said, they get rid of multi-head attention module with cross attention, the second one. Okay. And also with the decoder blocks used in GPT have only positional encoding, masked multi-head at self-attention, and feed-forward networks with add-in and layer normalization. Basically, it means that they don't have multi-head attention module with cross attention. They have removed that. Okay. And so here also, as I said, we have masked multi-head attention. So we don't have the future words. We don't condition on the future words. So it's not bidirectional, and it conditions only on the previous words. So it's a causal model. And the objective of BERT was what? Predicting a masked word in a sentence, right? However, GPT model is used for language model. What is language model? It predicts the next word. So you give a paragraph or a sentence to a language model, it gives you the next word. This is a language model in NLP. So this is exactly what GPT does. It always predicts the next word, right? And I think it's obvious because decoder of transformer does that. So the predicted new word is then added to the sequence and is fed to the GPT as input again. So you have the next word, it comes, and then you shift. You remember? The input of the decoder was the shifted output of decoder. Okay. Now I think you understand in ChatGPT, when you talk to ChatGPT, when you chat with it, it always remembers what you said. Why? Why does ChatGPT remember what you said? For example, I say, hi ChatGPT, I am Benjamin. Nice to meet you. It says, nice to meet you, Benjamin. It's very good. I'm glad to talk to you. And then you say, by the way, what was my name? It says, oh, your name was Benjamin, right? Because it remembers, because always we are feeding it as input again. Okay, that's one thing. And also in GPT model takes some document as and continues the text, right? So it continues the text, and again, it's unsupervised, or in other words, it's a self-supervised learning algorithm, because it can always, why? You always have some paragraph, take some paragraph, and you generate the next word. You know the next word. So for the training, assume you have a lot of data of internet. You take some paragraph from the Wikipedia, right? And then you just take the next word in one of the last words in the paragraph. So this is your training data. You generated the label yourself. You know which word you removed in the end of the paragraph. as how many paragraphs do we have on the internet? Infinite, right? So basically, they can use huge amount of internet data. Okay, and then after GPT-1, GPT-2 came, and GPT-3, they had more number of stacks and more learnable parameters. They were increasing, making it larger and larger. For example, GPT-2 had 1.5 billion parameters. What do I mean by parameters? Weights of neural network, right? 1.5 billion. Okay, they had a lot of servers, and much more then, because they said we have much more internet data, let's increase the number of parameters. And GPT-2 was trained on 8 million web pages. 8 million web pages, right? You can see how huge it was. So again, for embedded systems, we need to make them smaller. So we have small, medium, large, X large, and this still GPT-2. We have all of these versions. And also they have been used in a lot of things, such as dialogue systems, patent claim generation, medical text simplification, question answering, right? All of these things. Because in all of these things, you can implement them using generating the next word, right? Okay. Also, there are some papers which have discussed that. You can see it as few-shot learning, and a comparison of GPT and BERT can be found in this reference. Okay. By the way, GPT-3 is a very huge version of GPT. For example, GPT-2 GPT-2 has 1.5 billion parameters. NVIDIA Megatron has 8 billion parameters. Microsoft Turing NLG has 17 billion parameters, but GPT-3 has 175 billion parameters. You can see they are just competing by increasing the number of parameters. The richer you are, the more servers you have, the better you can get, right? At that time also, Elon Musk helped them, do you remember? So they had a lot of money. Okay, and so they have very huge amount of internet text data with various subjects. That's why in ChatGPT, you can talk about various subjects. You can talk about psychology, you can talk about sport, you can talk about anything, because it has been trained on all of these subjects. Okay. And also almost all topics, and some people are saying that it is passing the Turing's writer's test. By the way, this is GPT-3. GPT-4 also has come nowadays. And it's interesting that you can say that it has kind of memorized the tests of all subjects, but not in a bad way, which is overfitting. It has kind of memorized it, but not in an overfitting way. Okay. And because of complexity of huge number of learnable parameters, it could be done, and also big enough internet data. And some people are using it for fiction and poetry generation. So you can tell ChatGPT, ask it to generate some poems for you, and it does that. Okay, acknowledgement. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi and Professor Pascal Poupart at the University of Waterloo. And also you can see our tutorial paper, Attention, Mechanism, Transformers, BERT, and GPT Tutorial Survey. Okay, and these are the references. And by the way, as I said, GPT generates the next word every time. That's why when you chat with ChatGPT, what does it do for you? It generates word by word, one at a time, right? Does that. Initially, it was slower, so you could see it was generating one word at a time. But now they have improved the servers, and it has become fast. So it is generating one word at a time. And by the way, they have developed these, and nowadays they call these models large language models, LLM. Okay, and they also have improved them by some technique called reinforcement, human feedback with reinforcement learning, something like that. So what do I mean? Whenever you talk to ChatGPT, you can give feedback. You say, okay, it was a good answer, right? And then they have implemented some algorithm using reinforcement learning, saying that whenever you say it's good, it retrains, it fine tunes the weight and says, okay, it was good, it was a good answer. So they have used reinforcement learning for improving the model. Okay, let's go to the next topic. Any question? No? We covered one of the state-of-the-art algorithms in machine learning, in deep learning. Now we go to RBM, restricted Boltzmann machine and deep belief network. Okay, this was one of the most fundamental things in machine learning and deep learning. Okay, it was theoretical, it is theoretical, and it is fundamental. As I had said a lot in this course, Hinton loves this topic. It is the child of Hinton, right? Okay. Introduction. So centuries, by the way, you might be it might be interesting to you that restricted Boltzmann machine, deep belief network, Hopfield network, physics-based models such as Ising model, they are all related. They're all related to each other. We'll see. Okay. Centuries ago, the Boltzmann distribution, as you see, physics started. Boltzmann distribution proposed in 1868 is also called Gibbs distribution, proposed in 1902. Okay, they were proposed. Okay, so the energy-based distribution, it is an energy-based distribution, we'll see that, was found to be useful for modeling the physical systems statistically. Guys, listen to this because this is important. Someone won Nobel Prize for Ising model. Okay, this is a Nobel Prize winning thing. So the energy-based distribution was found to be useful for modeling physical systems statistically. One of these systems was the Ising model, which modeled interacting particles with binary spins. So the particles, they either rotate in this way or in that way, right? If I don't know if you have passed any courses on quantum mechanics and these things, they talk about the spins of electrons and these things. Okay, so yeah. So as I said, we have either clockwise or counterclockwise rotations of the spins, and I think you have seen these figures in physics, right? They say something like this in physics. Haven't you seen these figures? So these are the spins, and for modeling these, they have used Ising model. Okay, later the Ising model was found to be able to be a neural network. Interesting, can you see? So Ising model was proposed. Later someone said, let me model it as a neural network. And what was that? It was Hopfield network. Hopfield network was proposed, which modeled Ising model in a neural network for modeling memory. Hopfield implemented Ising model as a neural network, and he found out that it can model memory in our minds. The neural network can remember what it learned. Okay, it can memorize things, and it was proposed in 1982. One of my professors in Sharif University told us that Hopfield was going to win Nobel Prize for his contribution. So it was a big breakthrough at that time. Inspired by the Hopfield network, I think Hopfield is alive. Do you know how I know that? Because I wrote the tutorial on restricted Boltzmann machine, and inside that I had cited some papers, including the Hopfield network and Ising model. Several days after my submission to arXiv, someone emailed me, and who was he? He was the student of Hopfield. Hopfield is in Cornell University, as far as I know. He was also in Cornell. Said that these are some papers that of us that you haven't cited, and he had CC'd Hopfield. When I saw the CC of that email, I was shocked. I didn't know that Hopfield is alive, but Hopfield was CC'd in that email, and it was very onerous to me to receive an email from Hopfield and his student. Okay, so inspired by the Hopfield network, which was itself inspired by the physical icing model, Hinton et al. Proposed Boltzmann machine, or BM, and restricted Boltzmann machine, RBM, in 1983 to 1985. Now, I think you see the idea of that time. They were thinking about physics models, right? These models are energy-based models, and the names come from the Boltzmann distribution used in these models. Because in icing model, they use Boltzmann distribution, and also these are inspired by icing model, so they are using Boltzmann distribution. That's hence the name Boltzmann machine. Okay. During the winter of neural network, Hinton tried to save neural networks, and with the help of Max Welling, 2002 to 2004, they proposed, they improved Boltzmann machines, and they proposed a training algorithm for Boltzmann machines using maximum likelihood estimation. And BM and RBM can be seen as generative models, where the new values for neurons can be generated using Gibbs sampling. So generative models are very important models, families of models in machine learning. Guys, please listen. Generative models generate. So what is generative model in machine learning? I understand from its name, you will say, okay, it generates something, but how? Generative models, this is a simple thing in all generative models. They usually, you feed them some noise, it gives you some realistic data. And this data might be anything, might be image or something, okay? It depending on what data set you train on. So the simple idea behind all generative models is that they are fed with random noise, and they give you some important thing corresponding to that noise, okay? Hinton noticed that RBM can be a set of weights between a set of weights between every two layers of neural network can be seen as a restricted Boltzmann machine. We will see that. We will see that. Hinton said that, okay, then in year 2006, he proposed a greedy algorithm for training the weights of every layer of neural network using RBM training. And then he made that, so he stacked RBM layers a lot, so it could become deep neural network, and he named it deep belief network. Why? Because the energy which is passed from neurons to neurons in the restricted Boltzmann machine, we'll see the theory. I'm just talking to you about the idea. The energy is also called belief, okay? In machine learning, in physics-based models, the energy is also called belief. You can model belief as a probability, okay? So that's why they call it deep belief network. DBN, or deep belief network, allowed the networks to become deep as a good initialization for using backpropagation. And then, however, ReLU activation function and dropout were proposed in years 2001 and 2000. No, it's wrong. It was later, and 2014. And therefore, we didn't need RBM training anymore. And we could do only backpropagation without the need of regularization for overfitting. Okay. Now, Boltzmann distribution. Assume we have several particles, x1 to xd, okay, in a statistical physics. Guys, this is important. These particles, these are, for example, electrons and these things. Okay, these particles can be seen as random variables which can randomly have a state, and the states are either positive one or negative one, for example. Okay, for rotating counterclockwise and clockwise spins respectively. Okay, when I say counterclockwise a spin, it means that it rotates in a counterclockwise way. Okay, Boltzmann distribution proposed in 1868, or Gibbs distribution proposed in 1902. What does it do? It shows a probability that a physical system can have a specific state. What do I mean by a specific state? Assume I have these electrons. Okay, one of the possible states is +1, +1, -1, +1, -1. Another state is -1, -1, +1, -1, -1. All of these permutations, right? These are all states of the network. And this is 1D, it can be 2D, can be any. So you can see it as a graph. It can be mesh grid, any type of graph, right? And can you tell me how is this graph determined? By seeing whether the electrons are close to each other or not. Two close to each other electrons, they are connected in this graph. For example, these two electrons are close to each other, then these two, then these two, right? In 2D, for example, if it is mesh grid, it means that these electrons are next to each other, right? So I think it's obvious. Okay. Every of the particles has a specific state. The probability mass function, PMF, do you remember? PMF of this distribution is this. This is Boltzmann distribution. This is exponential operator. And this Z is a normalization constant. This is called also partition function. Okay, this Z is also called partition function. Ex here, what is this? This is the energy of the variable X. Okay, energy of the variable X. And beta is also some parameter which can be found. Okay, and then this is an important distribution. I don't know if you saw my optimization course or not, but in the meta-heuristic lecture also talked about simulated annealing. In that, I also mentioned the Boltzmann distribution. Boltzmann distribution is also used in simulated annealing. Why? Because simulated annealing is also a physics-inspired method. Usually, physics-inspired algorithms are using Boltzmann distribution. Okay, so the normalization constant is also called partition function, which is hard to compute. Why? Because it has summation over all of the possible states. Over all of the possible states. Why does it do that? It's similar to the idea of softmax. In the denominator, we need this summation over all possible states. So it sums to 1, right? And all of them are between 0 and 1. So it has a probability behavior, right? However, it's very hard to calculate this Z, right? Okay. We had this, the coefficient beta, which is greater than or equal to 0, is this. What is this? It's defined as 1 to the k beta t, which is proportional to 1 to the t. And what is T? T is the absolute thermodynamic temperature in kelvins. Okay. I don't know if you have passed any physics course or not. Physics 1, they talked about temperature and absolute temperature, right? This is not Celsius. This is Kelvin in kelvins, and in kelvins it can't get negative. Okay, so K beta is called Boltzmann constant. K beta is called Boltzmann constant. You will see how this is related to deep learning. Can you believe? You might be wondering how it is related to deep learning, but it is completely related. I will tell you. Okay, if the temperature T tends to absolute 0, well, if T goes to 0, what happens? Beta goes to infinity. Do you remember? So do you agree? Beta is 1 over T. If T goes to 0, beta goes to infinity. Then if you, in this PMF, if you set beta to infinity, what happens? P goes to 0. What does it mean? What is P? Probability. So it means that for the temperature 0, the probability goes to 0. That is why we rarely find temperature 0, absolute temperature 0 in the world. We can't find that. Maybe in some galaxies, NASA says it's very close to 0. Maybe it's 0.00001, but it never reaches 0 because the probability is very low. Right? Okay. By the way, in 0 temperature, it means that all particles, electrons and everything stop moving. The electrons even stop moving around the atoms, right? Okay. So it will be even cold for atoms. So recall these equations that we talked about. The free energy F beta is defined as this: minus 1 over beta ln of z. Ln is a natural logarithm, okay? And the internal energy is defined as this: So it's U beta, and it is defined as derivative of beta F beta with respect to beta. And F beta was the free energy, right? Okay, U beta, therefore, you just replace this F beta here, you will get this. If you take derivative, so according to the derivative of logarithm, you will have this. According to equation 2, which is this, according to this equation, so I'm replacing z, with this, and then I take derivative. So I will have this. And according to this equation 1, interestingly, we'll see that this is px. So basically I have this. U beta is this, equation 6. Now I'm repeating what I had. I have this is P, this is F, this is U, which we found. The entropy is defined as this. The entropy is minus sigma px ln of x. This is the definition of entropy, right? This is the definition of entropy. And then according to equation 1, so px here, I'm replacing this px with equation 1. So I will get this. Then I'm multiplying this to the terms. I will get these two terms. I have summation over px. What does it mean? Summation over all of the probabilities. So it becomes 1, right? Therefore, it gives me this. Okay. Lemma. A physical system prefers to be in low energy. Prefers to be in low energy. This is in thermodynamics, okay? Hence, the system always loses energy to have less energy. So when you have some energy in your system, it tries to lose energy to have less energy. It prefers to be in low energy, okay? Proof, on the one hand, according to the second law of thermodynamics, entropy of a physical system always increases by passing time. Entropy always increases. This is the second law of thermodynamics in physics. Entropy is a measure of randomness and disorder, right? Entropy, how disorganized I am, disorder in the system. On the other hand, when a system loses energy to its surrounding, it becomes less ordered. Okay? When you lose energy, you become less ordered. Hence, by passing time, the energy of system decreases to have more entropy, right? So energy goes down, entropy goes up. That is why when you put ink in water, the whole water becomes inky. Entropy is increased. Okay. According to equation 1, this is a Boltzmann distribution. And lemma 1, which said that we want to decrease the energy, the probability px of states in a system tend to increase by passing time. Why? We have energy here in the power of the numerator of P, right? When E goes up, what happens? Sorry, when E goes down, I said, according to this lemma, E goes down, energy goes down. What happens? The numerator, E to the minus beta E, when E goes down, this goes up. Then P goes up because this is in the numerator, right? I think it makes sense because we wanna, initially we have some states, but they change themselves in a way that they become more probable. They want to become more probable, okay? We'll use this idea. We'll see that Boltzmann machines use this. This corollary makes sense because systems tend to become more probable. This idea is also used in simulated annealing, where the temperature of system is cooled down gradually. In simulated annealing, also in knowledge distillation, the idea of knowledge distillation for passing information from a teacher's network to a student network, one of the algorithms uses the idea of simulated annealing. So they have temperature, they decrease it. So you can see it's used a lot in machine learning. They cool down the temperature, and you saw the theory for that. Why do they do that? Because they wanna lose energy and become more probable. Okay. Simulated annealing and temperature-based learning have been used in BM models. Okay. Recall the Boltzmann distribution. This was Boltzmann distribution, right? Now I'm going to talk about Ising model. Ising model, which won, as far as I know, won the Nobel Prize several years ago. Okay, Ising, recall the Boltzmann distribution. The Ising model, also known as the Lenz-Ising model, is a model in which the particles can have -1 or +1 spins. Therefore, xi is either -1 or 1, and I goes from 1 to d. I have d of them, d particles, right? The Ising model uses the Boltzmann distribution, which is equation 1, where the energy function is defined as this. So the energy function in the Boltzmann distribution is defined as this, minus summation of ij, jij, xi, xj. So this summation is over the pairs of the particles, right? And jij is some parameter which we'll talk about. And this energy is also called h, denoted by h of x, called Hamiltonian. The energy is also called Hamiltonian in physics-based learning. Jij is called coupling parameter. Okay. And the summation is over particles which interact with each other. Why? As I said, this is the summation over all of them. But for non-interacting particles which are far away from each other, in other words, in the graph, they are not connected to each other, this jij becomes 0. Right? So you can see the summation over only the interacting particles. Okay, note that as energy is proportional to the reciprocal of squared distance, okay, then nearby particles are only assumed to be interacting, because very far away particles are not interacting. Now you understand why I told you. You can see it as a graph where only close by electrons or particles are interacting, because when the distance is huge, the energy goes down between them. Okay, you have multiple things, multiple graph structures: chain, one-dimensional grid, mesh grid, lattice, closed chain, loop, torus, multi-dimensional loop. You can have various things. Based on the characteristic of a model, the coupling parameter has different values. If jij is greater than or equal to 0, it's called ferromagnetic. If you are electrical engineers, you have saw these in electromagnetics course. I myself have passed that course. It was a hard course. Okay, jij greater than or equal to 0 is ferromagnetic. jij less than 0 is called anti-ferromagnetic. Okay, if jij can be both positive and negative, it's called a spin glass. If coupling parameters or jij are all constant, it's called homogeneous. Okay. The BM and RBM are Ising models, the Boltzmann machine and restricted Boltzmann machine, which we'll see. There are Ising models, so there are special cases of Ising models whose coupling parameters, JIJs, are considered as weights. Can you believe that? So I'm modeling an Ising model in a way that JIJs become the weights of neural network, right? JIJs are the weights, and these weights are learned using maximum likelihood estimation. Why can I do it by maximum likelihood estimation? I told you, you can see energy as probability, as belief. And as you have probability, you can use maximum likelihood estimation. You can see it as likelihood, right? Hence, we can say that BM and RBM are energy-based learning methods. Interesting. It was proposed in 1974 to use the Ising model in neural network structure. Okay, Hopfield extended this idea to model the memory by a neural network, and it resulted in Hopfield network proposed in 1982. Okay, this network has some, so now in this slide, I'm talking about Hopfield network. This network has some units or neurons denoted by xi, I from 1 to d, right? So in Ising model, we had d particles, which might be electrons. In Hopfield network, we have d neurons. So the particles have been modeled by neurons. The states or outputs of units are binary. So in Ising model, each particle has a state, -1 or +1. In Hopfield network, each neuron has some output, and this output can be seen as a state, which is binary, +1, -1, right? And how do we obtain this? I think using some simple activation function, we can make it +1 or -1. Let Wij denote the weight of link connecting unit I to unit J. Okay, so by unit I mean neuron. Connecting from neuron I to neuron J, let it be Wij. Okay. Then the weights of Hopfield network are learned using Hebbian learning. Do you remember? We talked about Hebbian learning, or Hebb's law of association. So it's this: Wij is xi times xj, because xi and xj are either +1 or -1. If I is not equal to j, otherwise do not change Wij. Okay. After training, the outputs of units can be determined for an input if the weighted summation of inputs to unit passes a threshold. So it basically means that I have a binary activation function, right? So then what is this? You just asked me. This is O. This is the output of neuron. This is O that we had in perceptron and these things. This is the output. Yes. Well, O. Yeah. This is O, and this after checking with threshold, it gives me after activation function, right? It's either +1 or -1. Okay. In the original paper of Hopfield network, the binary states are 0 and 1. Doesn't matter. Okay, here we said -1 and 1. So the Hebbian learning was a bit different. He had modified the Hebbian learning to handle 0 and 1 rather than -1 and 1. Okay, Hopfield network is an Ising model. So Hopfield network can be seen as a special case of Ising model. So it uses equation 8, which was the energy or Hamiltonian as its energy. The energy is also used in Boltzmann distribution, which is equation 1. It is noteworthy that there are Hopfield networks with continuous states. So here we had discrete states. Continuous states, Hopfield has proposed it in 1984. Also, modern Hopfield networks, such as there is a paper in 2020, they are often based on dense associative memories. You can see this is a recent paper on Hopfield networks. Also, some other works you can see for Hopfield networks. The BM and RBM, Boltzmann machine, are restricted Boltzmann machine models, are Hopfield networks whose weights are learned using maximum likelihood estimation and not Hebbian learning. So in simple words, in summary, Boltzmann machines can be seen an Ising model where the coupling parameters are replaced by weights. Also, they can be seen as Hopfield network, as a special case of Hopfield network, where they don't use Hebbian learning. They use maximum likelihood estimation. Do you get? Now, let's go into RBM and BM. So see this figure. See this figure. Boltzmann machine is a generative model and a probabilistic graphical model, or PGM, which is a building block of many probabilistic models. Okay, many probabilistic models can use this as a building model. Its name is because of Boltzmann distribution used in this model, right? It was first introduced to be used in machine learning in 1983 to 1985 by Hinton, and then in 2002 and 2004 by Hinton and Max Welling. Okay, so what does it have? It has a layer, a visible layer, also called observation layer, V. We have D of them. So here you can see this V, right? We have D of them, V1, V2, V3 to VD. Okay, and the hidden layer, H, from H1 to HP. So the H and V, the visible layer and the hidden layer, do not necessarily have the equal number of neurons. So H1, H2 to HP, right? Okay, the visible layer is the layer that we can see, hence the name visible. So we can see. For example, it can be the layer of data. We have the data, so we can fit to it. The hidden layer is a layer of latent variables which represent meaningful features or embeddings for the visible data. Do you remember, for example, in autoencoder, we have latent space. So here we have latent layer. Okay, it gives us features. So I think now you understand what Boltzmann machine does. You give some data, it gives you some embedding for that data. And usually if you set P to be smaller than D, it can be seen as a dimensionality reduction algorithm, right? Because it reduces the dimensions. In other words, there is a meaningful or semantic connection between the hidden layer and the visible layer. Although their dimensionality might differ, D might be different from P. Each of the elements of V and H, visible layer and hidden layer, have a bias. Why? So here we have bias because we want to model intercept also, right? There are also links between elements of V as well as between the elements of H. What do I mean? So in addition to connections between H and V, I have connections between the neurons inside H here. Also have connections between neurons inside V. Okay, this is Boltzmann machine. Okay, let Wij denote the link between Vi and Hj. So Wij denotes the link between Vi, the ith node in visible layer, and jth node in hidden layer. Lij be the link between Vi and Vj. Here we have, where is Lij? Here, Lij, and also Jij be the link between Hi and Hj, J's, right? Bi be the bias link for Vi, here, this is B. And also Ci be the bias link for Hi, this is C. Okay? The dimensionality of these links are this. So you can see them as a matrix format. W, L, you put them in a matrix. J and B in a vector, and C in a vector, right? Note that W is a symmetric matrix. Why? Because Wij equals Wji, right? The weight connecting Vi and Hj is the same as the weight connecting Vj and Hi. Yes, it's kind of symmetric. Also, there is no link from a node to itself. So we don't have this. Do you understand? We don't have a link from a node to itself. We don't have this. Okay. As there is no link from a node to itself, diagonal elements of L and J are all zero. Lii and Jii's are all zeros, right? Okay. Hinton et al. Said there is do you see the difference of this figure A and one layer of neural network? What is the difference? Consider one layer of neural network and consider figure A. What is the difference? These J's and these L's are pain in the neck. Do we have weights connecting the neurons within a layer? So this is a layer of neural network, right? This is a layer of neural network, right? Do you agree? Okay. Do we have these? Do we have these? No, we don't have. So do we have these? No, we don't have. So Hinton et al. Said, let's get rid of J and L and simplify it. So we have only W weights, C weights, and B weights. Okay. Then it becomes like one layer of neural network, right? But they modified this. This was Boltzmann machine. They modified it. They restricted that by removing J and L. Hence, they named it restricted Boltzmann machine, RBM. Okay, they restricted that. So restricted Boltzmann machine doesn't have links within a layer. No, not have links within. So L and J are zero matrices. Okay. Recall that RBM is an Ising model. We told you, we talked to you, right? So it has energy or Hamiltonian like this, minus summation of Jij, Xi, Xj, right? And this is the energy of an Ising model, can be because of this, I can write it in this way. Can you see why? So I'm writing this in this way. What are my parameters? What are my Xi and Xj? Can you tell me? These are exactly the neurons, right? The neurons. So yeah, Jij's are the weights. The weights. So what do I have? What are the neurons here? V and H. What are the weights? So V and H are the neurons. My weights are W, C, and B, right? So here it is. I have Jij, Xi, Xj, and therefore I have B transpose V, right? I have C transpose H because of this form. I have V transpose H with the weights W. I'm writing this in matrix format, right? For example, here, this in this formula, this is Xi, this is Xj, and this is Jij, right? Also, for these, I only have one neuron because that's a bias. So this is energy between visible layer and hidden layer. And this energy is a scalar. Is a scalar. Okay. And now I use Boltzmann distribution. Okay. So I have a joint Boltzmann distribution. This is Boltzmann distribution. Let's put this energy equation 11 in the Boltzmann distribution. Therefore, I will have this 1 over Z in the Boltzmann distribution. 1 over Z, e to the minus e, and I have assumed I have dropped beta here. I assume beta is 1. Then what happens? I will have this. I'm replacing energy with equation 11, right? I have this minus here. Don't forget this minus. Okay, and this Z, what was Z? Z was summation of numerator over all of the states, right? So exactly, this is exactly what we have. Summation of the numerator, all of the states. So this is numerator, right? Over all of the states, all of the permutations of hidden layer and visible layer. According to lemma 1, what was lemma 1? We said the statistical model wants to reduce the energy, right? So Boltzmann machine and restricted Boltzmann machine try to reduce energy of the model. Okay, training the BM and RBM reduces its energy. So we reduce this energy. Okay. Now conditional distributions. Conditional independence of variables. In RBM, given the visible variables, the hidden variables are conditionally independent. What do I mean? Hi is independent of Hj given visible layer. Likewise, given the hidden variables, the visible variables are conditionally independent. So Vi is independent of Vj given H. So given a layer, the elements of the other layer are independent of each other, right? This does not hold in Boltzmann machine. Why? This is only in restricted Boltzmann machine. Because in Boltzmann machine, we have links within each layer. Because of the links, they can't be independent. Okay, here is the proof. So according to the Bayes rule, we have this. So PH given V, you can write it in this way. This is Bayes rule. And we can marginalize the denominator, right? I'm replacing these P with equation 12, which we found in the previous slide. Then I know that e to the A plus B, I can write it as e to the A times e to the B. This is exactly what I have done to simplify the terms. right? Then I know that this here e to the b transpose v does not have any h in it, the variable of summation. So I can bring it out of the summation. I factor it out, right? Then what happens? These two can cancel each other. This simplifies to this. We had this, okay? Now take this denominator as z prime. I define it as z prime. Then what happens? This p h given v will be 1 over z prime, this numerator. Okay, I write it in element-wise way. So this is inner product. I write it element-wise. Also, I write this element-wise. Then what happens? Exponential operator of summation becomes product of exponential operators. E to the a plus b, I can write it as e to the a, e to the b. This is exactly what I have done, right? Then the equation 14 shows that the visible variables, the hidden variables are conditionally independent. Why? From this equation, I can infer that the hidden variables are independent. Can you tell me why? Because I have product of likelihoods over the p hidden variables. When is it holding? When can I say the joint probability of some variables is a product of probability of each of them? When they are independent, right? This is exactly how. Therefore, given v, h's are independent. Likewise, we have the other way around. Given h, v's are independent. Okay. We can write similar expressions for p of v given h as here, and again, given hidden variables, the visible variables are conditionally independent. Now we had this, equation 14. Good. We had this, I'm repeating it here. Consider also this, ph given v, you can see that p, h and v over p of v. Right? This is the formula that we have also used in Bayes rule and this is. So here, according to these two, if you compare these two, you can see that I can see this z prime as pv. Also, I can see this as p joint probability of h and v. So I can write it in this way. Right? Therefore, I can see this as a joint probability of phj and v. Why phj only? Why phj only? Because here is for the jth hidden variable. For the jth hidden variable. So I have it here. Also, I can write this term element-wise. Guys, do you follow me? Since to me that you're not following. No, don't follow me. No. Which, okay, until where did you get lost? This is okay. So this was proof, and then we just had it in question 14. We just derived. Do you remember this? We just derived this. I'm repeating it here. Repeating it here. Okay. Then, do you agree? This is Bayes rule. pH given v equals pH and v over p and v, p of v, right? Do you agree? So far clear? Then compare these two. Compare this and this. So I can see 1 over z prime as 1 over pv. I can also see this term as p of h and v. Right? Okay. I have p of h and v, but here I can write it as p of the product of j from 1 to p of hj and v. Do you agree? hj and v, right? Therefore, this term inside the product, I can see it as p of hj and v. This is exactly what I have done in equation 16. So far clear? You need to be patient with mathematics of these things, because at the end, you'll see how they match. If you are not patient, you will get lost. Come with me step by step, okay? Similarly, according to equation 15, this is what we found in equation 15. I'm repeating it here, right? Again, I use the base rule. Again, for the other way around, I'm doing that. P of V given H, right? Likewise, I can write P of H and VI as this. So previous one was P of HJ and the whole V. This is P of the whole H and VI, right? The joint. So equation 18 is the joint probability of the whole hidden variables and the ith visible variable. Equation 16 is the joint probability of jth hidden variable and the whole visible variables, right? This is whole visible variables, V1 until VD, but this is only HJ. This one is the whole hidden variables, H1 to HP, but this is VI only, okay? Why did we derive this? You might be wondering why. We will use these equations later, okay? We'll use them later. Sampling hidden and visible variables. Okay. We can use Gibbs sampling for sampling and generating the hidden and visible units. Okay. So what do I mean? In restricted Boltzmann machine, I have some distributions. Then I sample in each layer, hidden variable and visible variable. I can sample from this distribution. So each layer has some distribution, I sample. Why? As I said, we have beliefs, we have energies. Energies can be seen as beliefs, right? A probability by Boltzmann distribution. So I can sample from it, right? By Boltzmann distribution, we found the probabilities in the previous slides. Now let's use them. So from P of H given V, I can sample H. From P of V given H, I can sample V. And I do it iteratively, alternatively, until convergence. This is exactly called Gibbs sampling. Why? What is Gibbs sampling? Gibbs sampling is very simple. It says, assume you have several variables. There is a joint distribution for all of these variables, and you want to sample from them. It's very hard. I can't do that. Let's simplify. Let's relax the problem. Let's say that I only assume the first variable is random variable and all of other variables are fixed. So conditioned on all of the other variables, I sample from the first, the distribution of first variable. Then I only consider, after that, I only consider the second variable as random variable and I condition on other variables. Then I only sample from the third one, conditioned on all of them. And I do it until the end. And I repeat it. I repeat it until convergence, until the sample is the same. It doesn't change, right? This is called Gibbs sampling. In optimization, alternating optimization has the same idea. You have some optimization variables. It's hard to optimize over, for example, you have two optimization variables. It's hard to optimize over both of them. First, fix one of them. Take derivative of cost with respect to one of the other variables. Assume the other one is fixed. Optimize, maybe by gradient descent or closed form solution, whatever. Then go to the next one. Assume the other one is fixed and optimize with respect to the other one. Then do it again. Do it again until they don't change, until convergence. So this idea is repeated in various fields of science, alternating optimization, Gibbs sampling, and these things, right? So Gibbs sampling is this. Why is it Gibbs sampling? Given V, I assume V, visible variable is fixed, visible layer is fixed. I sample from H. I assume H is random. Then I assume H is fixed. Then V is random, visible variables. Then I sample from that. And here, nu is the iteration index. So I do it until convergence. The convergence in Gibbs sampling is called Bernstein convergence. This is just naming, okay? In Gibbs sampling, only several iterations of Gibbs sampling are usually sufficient. Can you believe that? They're very fast. Some papers even have done only one iteration. They are very fast. After the burning, samples are approximate samples from the joint distribution P of V and H. So we'll have some samples, right? Some samples V and some samples H. Finally, after convergence, you can assume that the V's that you have sampled and the H's that you have sampled are from the joint distribution of P of V and H. This is the algorithm of Gibbs sampling in restricted Boltzmann machine. What do? We have a visible dataset V, which we introduce to the visible layer, right? Then the hidden layer also is random here. So this sampling can be implemented in this way. I have visible dataset V, initialization, some optional, right? Get initialization or do random initialization of V. Okay. Then what do? We have a while loop. Then for P, for J from 1 to P, what do I mean? For all of the hidden variables. For hidden variable 1 to hidden variable P, I have a for loop. I sample each of them. H1 to HP. Then after this, so this is basically sampling all of the H's, H vectors. And then I sample P of H given V. Then I sample V, P of V given H for all of them, for all of the visible variable 1 to visible variable D. Okay, this is Gibbs sampling. This is basically what we are doing. And how can we do that in this algorithm? How can we implement this? Can be implemented as drawing a sample from uniform distribution and comparing it to the value of probability density function, this. So in computer, when you want to sample from a distribution, either you can, if you have this, you can use the inverse of CDF, okay? Inverse of CDF. For more information, see my tutorial on sampling algorithms, okay? Or you can simply generate a number between 0 and 1 and compare it to the probability. If it is less than the probability, then it means that you accept it. Otherwise, you reject it, okay? Implementation of sampling VI has a similar procedure. We do it alternatively, okay? Gibbs sampling for generating both observation and hidden units is used for both training and evaluation. So far, we saw a lot of things. One of them was sampling, right? But why? Why do we sampling restricted Boltzmann machine? Because we want to use these samples for training, right? And also for evaluation. We'll see that, okay? Use of Gibbs sampling in training RBM will be explained later, okay? How we are going to use it. After the RBM is trained, now the test phase. In the test phase, why sampling is useful? We can generate any number of p-dimensional hidden variables as meaningful representation of d-dimensional observation. So after assume using samples that I sampled, I train restricted Boltzmann machine. Then it is a dimensionality reduction algorithm. You feed your data to the visible layer, you sample from the hidden layer. Every time you sample, you will get some semantic embedding, some useful embedding. Once this is a good embedding, another one, oh, it's a good embedding too. Another sample, it's a good embedding too. They are different samples, but they're all good. They're all semantically related to the visible layer, to the data. Do you get it? Moreover, using Gibbs sampling, we can generate d-dimensional observations in addition to the original data set. What do I mean? So once in the previous paragraph, I said you feed the data to your visible layer, you sample hidden embeddings. You can do it the other way around. So you feed data to the visible, you sample from the embedding, and then vice versa. You can sample the visible layer again. It means that you have some visible layer, some data set, you generate another data set which is similar to that. You generate another data set. You generate a data set similar to your data set. You can use it for anything you want, such as data augmentation. Right? Interesting. So it's a generative model. Now training restricted Boltzmann machine by maximum likelihood estimation. The weights of links, which are W, B, and C, should be learned, right? We don't have them. In sampling, we assumed we have them, right? Okay, we should be learned so that we can use them for sampling and generating the hidden and or visible units. Consider a data set of n visible vectors. So we have visible vectors at first from the data set, right? And we have n visible vectors, n data points, each of which is d-dimensional, right? It's a data set. Note that VI should not be confused with VI, where the former is the ith visible data and the latter is ith visible unit. What do I mean? Don't confuse bold VI and not bold VI. What is not bold VI? Is the ith visible unit, right? Bold VI is the ith data point, which is d-dimensional. Okay? Don't confuse these two. What do I mean, ith data point? I have a data set, n data set, each of which is d-dimensional. Okay. So VI, you can see it as this. VI1 to VID. Okay. Now, log likelihood of visible data. I think it's obvious for you. What we are going to do? Maximum likelihood estimation. What it means that we have some parameters, W, B, and C. Let's learn them so it maximizes the likelihood of data in the visible layer. Do you see? So the log likelihood of W and B and C. What is that? Summation of log of P of VI. P of probability of visible layer. Right? I can marginalize this by summing over all of the hidden variables. What do I mean marginalizing? Do you agree that P of X and Y over all of the Y's is P of X? Do you agree with this? This is called marginalization over Y. Because I'm summing over all of the possible values of Y. So it cancels out the impact of Y, right? Here exactly I'm doing that. I'm summing over all of the variables of H. Then what do we have? This is exactly the joint distribution, which is a Boltzmann distribution, right? According to equation 12. And then 1 over Z is a constant. So I can factor it out from the summation. Right? Guys, please don't give up. I see some of you have given up. It's very interesting topic. I don't know why you have found it boring. Do you know how many papers I read to write this tutorial and also write this lecture? I read a lot of papers to simplify it. It's the simplified version. Okay. I read a lot of papers to simplify. So please come with me and you'll see it's very interesting. When I learned that, I was dancing. So 1 over Z is a constant, okay? I can factor it out from the summation and bring it out of the summation. 1 over Z here, right? So I can bring it out. Then what happens? Then I know that logarithm of A over B, you can write it as logarithm of A minus logarithm of B. This is exactly what I have done, right? Then what do we have? This logarithm of Z is a constant, so I can bring it out of the summation. Then I will have summation of 1, which is n, right? So I will have this. Then, according to equation 13, I'm replacing Z with what I had. Do you remember Z? We found it. The constant, the partition function. We found it, and it was this. Right? I'm replacing it here by equation 13. We found this. I'm repeating it here. I'm repeating what we found. Okay. We use maximum likelihood estimation, or MLE, to find the parameters W, B, and C. I named them theta. Okay. So what should we do? Take derivative, set it to 0, right? Or if we can set it to 0, closed form solution, that's fine. Otherwise, we need to do gradient ascent or something. The derivative of log likelihood with respect to parameter theta is this. So this term is derivative, the first term, right? And this is the second term, is derivative. Also, n is a constant, so it comes out of the derivative. We found this. Okay. The first term of the derivative, this one. This is the first term. Okay, what is this? Derivative is a linear operator. It can go through the summation, right? And then, let me recall. Okay, derivative of logarithm, according to this formula, is derivative is 1 over the argument times its derivative, right? Its derivative. This is, I'm using the formula of derivative of logarithm. Then what happens? Okay, then I'm passing the derivative through the summation and I'm using the derivative of exponential operator. Then I get this. This is the derivative of exponential operator, right? Then what is this? Can you tell me? This is exactly the definition of expectation. This is the definition of expectation. So I can replace it with the definition of expectation, right? Can you understand why? Pio, just give me a second to think. So this is the argument of expectation. Okay. And what is this? What is this that I'm circling around? This is exactly probability. Probability times the argument. This is expectation. Expectation of this term, right? This is what we found. I'm repeating it here. Okay, this is what we had. And now the second term. So with the first term, we talked about it. Now the second term. Let's go to the second term. Where is the second term? So the second term is this. Let's simplify it. Again, I have derivative of logarithm. So I'm using the formula of derivative of logarithm. Here, I take this. Okay. Now derivative is a linear operator. I can pass it through the summations in the numerator. Then I use the derivative of exponential operator to get this. Okay. Again, this is definition of, by definition, it is expectation. Right? So in summary, I put the simplifications of the first term and second term together. It gives me equation 25. Okay. What is this? This is the derivative of log likelihood. Okay. Setting this derivative to 0 does not give me a closed form solution, unfortunately. So I need to do iterative optimization. In maximum likelihood estimation, we want to maximize it. So we use gradient ascent with this gradient. Okay, so this is what we found, and this is the energy. But I assume that theta is the optimization variable. I have 3 optimization variables now. W, B, C. So we need to calculate this for all of them. Let's do that. Derivative of this minus, so the derivatives with respect to these parameters in equation 25, which is this. So I have this derivative of this term with respect to W. So this is, according to equation 11, this was minus energy, right? This was minus energy in restricted Boltzmann machine. I have derivative with respect to W. If you take derivative of this term, these are constant, they go away, you will have VH transpose. Also this term, take derivative with respect to B. These two go away, they are constant, this becomes V. Again, with respect to C, these two are constant, they go away, this becomes H, right? So therefore, so I'm using these now in equation 25, which is here. for each of them. If you do that, the derivative of log v with respect to w becomes this. So what we just calculated these terms. Do you agree? These terms, I just calculated them here. These terms inside the expectation. Now let's put them back inside the expectation for each of them. For the w, it was vh transpose. Okay, and v here I'm conditioning on v. So v is not a random variable. So it can come out of expectation. So vi comes out of the expectation. Also here, however, v is a random variable. This is the joint distribution of v and h and v. So v cannot come out. Do you see the difference? Here it was conditioned on v. So it can come out of expectation. In the second term, it is joint distribution of h and v. It cannot come out of expectation. Also for b, so I have v. Do you remember? I had v. So I replaced them with v inside the expectations. I know that here I'm conditioning on v. It can come out of expectation, so we'll have vi here, but it cannot come out. For c, it was h. It was h. So I have this. I can simplify it. Now I'm repeating what we had. We had these. Okay. Now I'm defining. So here, I'm defining this to be hi hat, expectation of h with respect to probability of h given vi. I define it to be hi hat. It's my notation, just for the simplification in equations that I had found. So then the expectations, these two expectations are replaced by hi hats. Okay, so now these are the derivatives I'm going to use for maximum likelihood estimation. Again, they do not give me a closed form solution. Gradient ascent we should use. In the derivatives of log likelihood, we have two types of expectation, right? We have two types of expectation. The conditional expectation, right? This is the conditional expectation. And also the joint expectation. These are joint expectations. However, they has nothing to do with the observation and merely about the RBM model. Do you agree? The joint distribution does not have anything to do with the observation. It's merely about the RBM model, because the observation model, the observation here is just our data. It's not random. The RBM is random. Okay, you get it? So I talked to you about the derivatives for maximum likelihood estimation. Now another important thing in RBM is contrastive divergence. I'm building a building for you gradually. Just come with me. Okay, we had this equation 23. This was a derivative of log likelihood for some parameter theta, right? The conditional expectation, which was this, do you remember? I defined it to be hi hat, includes one summation. Why? Why? Expectation has summation in its definition, right? Okay. Moreover, according to equation 24, what was equation 24? Let me go back. I don't memorize these. So I'm like you, I'm just learning, we are learning together. Equation 24 was this, right? Which was the second term of derivative of log likelihood. So here it was, and we found this to be like this, okay? The joint expectations used in equations 27, 28, and 29, which were these, contain two summations. Why? Can you tell me? Because of these. Do you see these two summations? So I have two summations. So this had one summation, but these have two summations, okay? The double summation that we had, and what was the double summation? One of them was on the visible variables, one of them was on the hidden variables. The double summation makes computation of the joint expectation interactable. Do you know what this double summation means? Summation over all possible values for visible variables and all possible values for hidden variables. And if they are continuous variables, it is mind-blowing. Right? The first is 0.1, 0.2, 0.00, 0.1, I don't know, 0.001, something. This is one possible. Another vector, another possible vector. You have infinite number of variables possible for continuous, right? For discrete, it's better, but it still is interactable. So what should we do? We need to do something about it. So therefore, exact computation of maximum likelihood estimation is hard. We can't do that. We should approximate it. Okay. One way to approximate computation of joint expectations in MLE is contrastive divergence. It was proposed in 2002. Contrastive divergence improves the efficiency and reduces the variance of estimation in RBM. I will tell you what it is. The idea of contrastive divergence is this. First, we obtain a point V tilde using Gibbs sampling, starting from observation VI. Then we compute expectation by using only that one point V tilde. Did you get what I mean? So first, we obtain a V tilde, a visible variable by Gibbs sampling, 1 point, right? From the observation VI. So what do I mean? You feed the observation VI in the data set to the RBM, then you can sample both visible layer and hidden layer, right? Sample the visible layer once. It gives you V tilde. Use that V tilde for the computation of expectation, only that one, rather than all possible values of V, right? Okay, this is contrastive divergence. What is this? The intuitive reason for why contrastive divergence works is this. We need to minimize the gradients to find the solution of MLE, right? We are maximizing the likelihood. So we are using gradient ascent, right? In both gradient ascent and gradient descent, the gradient becomes smaller and smaller, right? In the optimal solution, gradient is zero. So we need to minimize gradients to find the solution. In the joint expectations, equations 27, 28, 29, rather than considering all possible values of observations, which is hard, contrastive divergence considers only one of the points or observation, only one of them. If this observation is wrong belief, which we do not wish to see in generation of observations by RBM, contrastive divergence is performing a task which is called negative sampling, right? In negative sampling, we say rather than training the model not generate all wrong observations, we train it iteratively but less ambitiously in every iteration. Each iteration tries to teach the model to not generate only one of the wrong inputs. Gradually, the model learns to generate correct observations by avoiding to generate these negative samples. I read this because I don't memorize the slides. I need to read it once and then I explain it to you. So what do I mean? This idea of negative sampling. Try to learn techniques in this course, okay? I'm teaching you the techniques. I'm teaching you how to fish rather than I give you the fish. One of the important techniques in probabilistic machine learning is negative sampling. Contrastive divergence is using negative sampling idea. What is negative sampling? It says that rather than, so in probabilistic models, we usually train the model to generate good samples and not to generate bad samples, right? So I have negative samples. It means that don't want to generate them, right? However, negative samples are a lot. I have a lot of huge possible values that are not in the data, right? So positive samples are usually smaller. Negative samples is huge. how can I sum over all of the possible negative values? I can't. What do I mean by summing over all possible values, negative values? It means that I want to tell the network or the RBM or the model, hey model, do not generate all of these. Do not generate all of this. It's intractable. Rather than that, I relax this problem, say that I only take one of the negative samples, one of them. And I say, hey model, in this iteration, learn not to generate this negative sample. In the next iteration, I take one other negative sample. I say, hey model, now in this iteration, learn not to generate this negative sample. After several iterations, it knows that it shouldn't generate a lot of negative samples. Then it learns the thing. Did you get it? This is the idea of negative sampling. In other words, for example, I want to teach a baby what cucumber is. Okay. In fact, rather than saying that, bringing the whole world, excluding cucumber, and say, hey, baby, these are all things which are not cucumber. Table, this phone, these are not cucumber. Rather than this, no, I do it iteratively. And in each iteration, I take it easy to the baby. I know that would be overwhelming to the baby. But now I say, hey, baby, this is pen. This is not cucumber. In the next iteration, hey, baby, this is phone. This is not cucumber. Hey, baby, this is tomato. This is not cucumber. After 1 million iterations, baby can discriminate cucumber from the negative samples. Okay, this is what we are doing. Let H tilde be the corresponding sampled H to V tilde in Gibbs sampling. Okay, so V tilde was one observation and H was one hidden variable, right? And these are sampled by Gibbs sampling, right? According to the above explanations, contrastive divergence approximates the joint expectation in the derivative of log likelihood, equation 25, by Monte Carlo approximation. What is Monte Carlo approximation? Don't be afraid by these names. These are very simple. Monte Carlo approximation simply means that randomly sample from your data, and the more sample size you have, the better it is. For example, you want to sample from a distribution. So we have Monte Carlo sampling and we have Monte Carlo approximation. Monte Carlo sampling simply means that you sample from the distribution. The more you sample, the more you know about that distribution. Okay, that's one thing. Monte Carlo approximation says that you can approximate expectation by mean. By mean. For mean, for calculating mean, you need some sample, right? What is mean? 1 over n summation of xi's. So you need some xi's. N is the sample size here. If you increase the sample size, Monte Carlo approximation gets better. So it more accurately approximates expectation. This is called Monte Carlo approximation. Okay. So here, we are doing Monte Carlo approximation. Why? Because we have expectations evaluated at VI tilde and HI tilde for the ith observation and hidden units, where VI tilde and HI tilde are found by Gibbs sampling. Hence, this is exactly Monte Carlo approximation. See, I'm replacing this expectation by mean. Do you see that? Okay. Experiments have shown that a small number of iterations in Gibbs sampling suffices. Even some papers have done 1 iteration. By the approximation in equation 30 that we had, then we can have VI tilde rather than the expectation that we had. Recall equations 27, 28, and 29. Where was that? Here. We had these expectations. This expectation. Now I'm doing Monte Carlo approximation. So they are simplified to these. These equations make sense. Why? Let's interpret, let's analyze this. Why do they make sense? Now we came in this highway with went and we derived the formulas. Now let's analyze them, see whether they make sense or not. Yes, they make sense because of this. When do, in maximum likelihood estimation, we are using gradient ascent. And in gradient ascent, at the end, the gradient becomes 0. Because the optimal solution, first order optimality condition, the gradient becomes 0 at the optimal solution. When do they come 0? Set this to 0, set this to 0, set this to 0. When? What is the difference of this term and this term? Vi and Vi tilde. What is the difference of this term and this term? When Vi and Vi tilde. What is the difference of this term and this term? Hi hat and Hi tilde. So whenever Vi tilde becomes similar to Vi and Hi tilde becomes similar to Hi hat, we are done. Exactly what we are doing is this. We want to estimate the visible variable and the hidden variable. Right? This is exactly makes sense. Also, in some papers, Hinton's papers, if you go and see the Hinton's papers, he writes these equations in this way. It took me a while to understand these equations. I think it was his paper in 1986, something like that. In that paper, he wrote them in this way. Okay. These are expectation over data and reconstruction of data. Okay. This is the algorithm of training RBM using contrastive divergence. Let's go and see. Okay. We have some training data, x1 to xn. Randomly initialize W, B, and C because I want to do gradient ascent, right? Then I have loop for, you tell me, training the gradient ascent. Then sample a mini batch, V1 to VM, several visible points from the training data set. Note that M, we may set M equal to N. What do I mean? When we set M is the batch size, N is the total number of points. So we can have only one batch. So it can be the full gradient descent, full gradient ascent. If M is less than N, then we have mini batch, a stochastic gradient ascent. Okay. Then we do Gibbs sampling for each data point. What do we do? Initialize the V hats by V's. So initially, my estimated V hats are the input data, V's. Then for points, for each of the points, I from 1 to M, for each of the points, what do? We have, what was algorithm 1? It was for Gibbs sampling. Do you remember? So we use last iteration of algorithm 1. What do I mean by last iteration? Last iteration of Gibbs sampling after convergence. So the last iteration is a good sample, right? So it gives me some HIs and VIs, the hidden variables and visible variables. Then I put them as a vector and I denote them by H tilde and V tilde. I also calculate this expectation. You can use Monte Carlo approximation to give me H hats. Now I calculate these gradients using the formulas that we found, right? Then you update them by gradient ascent. It should be gradient ascent, I think. I made a mistake here. These are plus. Okay. Did you get it? Now Boltzmann machine. So we talked about restricted Boltzmann machine. Now Boltzmann machine. The only difference was what? The weights between the neurons within a layer, every layer. So I have L and J also. In restricted Boltzmann machine, we had only W, B, and C. Now 2 other variables are added, J and L. Again, you can calculate their derivatives, and these are like this. They're very similar to before, but 2 other additional gradients. Then you also calculate this, use them in the gradient ascent in order to find optimal L and J. That's it. The difference of RBM and BM is this. Interesting. Deep belief network. We can train a neural network using RBM training. Okay, by the way, in this slide deck, the hard part has passed. Now, take a good breath, and it's passed, okay? I think finally you saw that the formula was easy. The derivation was a bit hard, okay? Now, let's use them for neural network. We can train a neural network using RBM training. RBM, and that was proposed in 2006 when Hinton wanted to save neural networks from being forgotten in machine learning because it was losing the competition with kernel SVM. So it was published in Science journal. Okay. Training a neural network using RBM training can result in a very good initialization of weights for training network using backpropagation. Okay. Then what do we have? Before the development of ReLU and dropout, multi-layer perceptron networks could not become deep. Why? Because of gradient vanishing. Then Hinton said, let's pre-train neural networks using RBM. It gives you some weights, and then use these as initialization for backpropagation, and it works well. So fine-tune them using backpropagation. Do you get it? So basically, what Hinton said is this. Assume you have these number of L-1 layers in a neural network with L-1 layers, sorry. It depends on what you define by layer, because this is a bit confusing. If you consider the weights between every layer as one, every two layers as one layer, then it becomes L-1 layers. If you consider each of these as layer, then it becomes L layers. Doesn't matter. Naming is not important. Okay, mathematics is important. Here, I consider every two layers as one RBM. Right? Do you agree? Then this is RBM2. As you see, RBMs are overlapping. So the hidden layer of one RBM is the visible layer for the next RBM. The first RBM, the first layer, which is the first RBM, is observation layer, is visible layer, is the data. Then each other layer is RBM, its visible layer is the hidden layer of the previous RBM. Right? Then we do it, then we train it by maximum, each layer by maximum likelihood estimation. What does maximum likelihood estimation do? It gives me optimum W, B, and C. What are W and B and C? These are the weights of each layer, W1, W2 until WL-1. Also, B and C are the biases, right? Then, so I do it. So first I train this, then I train this, then I train this until the end. I train all of them. This now I use these weights for initialization of backpropagation. Because of this good initialization, I can make it deep. This was before introduction of ReLU and dropout. Using this, we don't face gradient vanishing anymore. As I said, I think I already talked about this slide. So you can see this network as a stack of RBM models, and they named it Deep Belief Network, or DBN. Why? Because it's based on belief, Boltzmann distribution. Okay. And this is training a deep belief network. So you can see we are, this is training data. We have a pre-training by Boltzmann machine. What do we do for each layer? So per each layer, if it is the first layer, the visible variables are the data set. Otherwise, we should generate n hidden variables for the of the previous RBM, right? What do I mean? This is an important thing. So for the first RBM, the visible variables are known. This is data. What about the second RBM, the second layer? What should I do? I don't have the feasible variable. How can I do that? I can sample it. How? I can sample the hidden variables in RBM1. If I sample the hidden variables in RBM1, it can give me the visible variable for RBM2. Do you get it? Let me repeat. In RBM1, layer 1, the visible variables are known, data. For RBM2, I don't have the visible variable, but I can sample using GIP sampling. I can sample the hidden variables in RBM1. It gives me the visible variable for RBM2. I do it for other RBMs as well, right? Then I use algorithm 2 for training WB and BL and B. See, here BL is B, BL plus 1 is C. Do you remember we had B and C? Right. Okay. Then we initialize network with the weights, and then we do backpropagation. Also, Hinton used that for dimensionality reduction. So he trained an autoencoder. So in his paper 2006, he used that for dimensionality reduction. He said, I have encoder and decoder, and each of which can be seen as a stack of RBMs. So in the middle, I have a code layer or latent layer, right? Okay, some acknowledgements. This slide deck is based on our tutorial paper, Restricted Boltzmann Machine and Deep Leaf Network, Tutorial and Survey. Okay, it has also appeared in our textbook, Elements of Dimensionality Reduction and Mindful Learning. For more information on RBM and DBN, refer to our tutorial paper. There are more things in that paper, okay? There are more things. For example, we have Deep Boltzmann Machine. I didn't cover that. Deep Boltzmann machine. It's different from deep leaf network. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. Also, some slides of this slide deck, especially the icing model part, are inspired by the teachings of Professor Mehdi Mulkarai at the University of Waterloo in the Department of Statistics. He also taught me a lot of things in this area. Okay, these are the references. Okay, let's come back, have a break, and come back at 9:30, and then we'll continue. Thank you. Thank you. Guys. Okay, so deep metric learning. Now we shift gear and we talk about deep metric learning. So, introduction, both spectral and probabilistic metric learning methods are these. So guys, please listen. I also have said this in a statistical machine learning course, especially in KNN lecture. I talked about it a bit. So Euclidean distance is not optimum, okay? Therefore, people came up with something named Mahalanobis distance. I talked about it. I'm not gonna talk about it here. And then people generalized that in order to have generalized Mahalanobis distance. And this is exactly generalized Mahalanobis distance, and this is a squared generalized Mahalanobis distance. And this matrix W is a parameter, okay? And if you set W to, guys, I need to concentrate. If you set W to identity matrix, what happens? This generalized Mahalanobis distance becomes Euclidean distance, right? And so, by the way, W needs to be positive semi-definite for this to satisfy triangle inequality and be convex, okay? To be a metric, distance metric. So this is what spectral and probabilistic metric learning do. However, deep metric learning throws away this equation. It says it doesn't use that. It has a different approach. What do they do? They usually do not use a generalized Mahalanobis distance, but they learn and embed in a space using a neural network. Okay. And what does this embedding space do? It maybe either makes the representation of data better, or it discriminates the classes better. So in this way. So the network learns a p-dimensional embedding space for discriminating classes or the dissimilar points, and also making the similar points close to each other. So basically its idea, if it is supervised, its idea is what? Is like the idea of Fisher discriminant analysis. If you have seen my course, the statistical machine learning course, FTA, I have talked about it. FTA, so Fisher says what? Let's decrease the intra-class variances and increase the interclass variances. This discriminates the classes. You can do it in deep metric learning too. Okay, this is one thing. If it is unsupervised, then what does it mean? It means that the similar points should fall close to each other. These similar points should fall away from each other, right? Because we have a patterns of data then. Okay, then any distance metric which gets p by p-dimensional, so two p-dimensional vectors, and it gives you a scalar, can be used in this embedding space, right? In the loss function of network, we can use this distance function in the embedding space. Why? For example, I wanna use a loss function, which I said the distance of the similar points should be small. The distance of dissimilar points should be large. So I should use this distance metric in the embedding space. Okay. F here is what? Assume it's a network, deep neural network. Okay. And f of xi is the output of the neural network for the input xi. It's a p-dimensional vector, right? So the distance between xi1 and xi2 is this. So xi1 and xi2 are 2 points. I feed them to the network. It gives me these two, fxy1 and fxy2. This is a distance between the embeddings of the 2 points in the embedding space. Okay. We train the network using mini batch methods such as the mini batch stochastic gradient descent, and denote the mini batch by B. Assume B is the mini batch size. The weights are the learnable parameters theta. Okay. One of the deep metric learning methods is reconstruction autoencoder. What do we do? An autoencoder is a model consisting of encoder and decoder, E and D. There are several types of autoencoder. All types of autoencoder learn a code layer in the middle of encoder and decoder. So it's latent space, right? We have inferential autoencoders. What do? They learn a stochastic latent space in the code layer between the encoder and decoder. What do I mean? Inferential autoencoder is this. E, we have D. Here we have a distribution, okay? Then I give X, it gives me some parameters in this distribution, right? So for example, if this is Gaussian, what does it have? Mu and sigma, right? It gives me mu and sigma. So it gives me some distribution. Then from this distribution, I sample something like Z. I call it latent factor, okay? Then I feed this Z to decoder. It gives me X hat. And X hat is the reconstructed X, right? This is called inferential autoencoder because they're probabilistic. Invariance is related to probability. Some examples are variational autoencoder and adversarial autoencoder, which we will cover in this course. Okay, adversarial autoencoder is based on GAN, generated adversarial networks. Okay, another type of autoencoder is reconstruction autoencoder, which is not a stochastic. What does it do? It has encoder, you feed, so encoder, decoder, you feed X, it gives you some E of X, you feed E of X to D, it gives you X hat. There is no sampling, distribution, and distance. Okay, and this E of X is what? An embedding, a good representation, compressed representation for X. We denote the input by X, D-dimensional, okay? And then, as I said, we have E of X, P-dimensional embedding, and then we pass it, feed it to the decoder, it gives us X hat. Okay, if P, the dimensionality of latency space, is greater than D, then we have overcomplete autoencoder, which is this. If P is smaller than D, then we have this. This is called undercomplete autoencoder. See the difference between these two. Okay. The last function of reconstruction autoencoder takes the tries to make the reconstructed data close to the input data. So the distance between X and X hat should be minimized, right? Maybe with some regularization term, where lambda is the regularization parameter. For example, we can use mean squared error by using squared Euclidean distance as D, right? Also, denoising autoencoder uses overcomplete autoencoder. So here, what does it do? Sorry, E, D. It gives X plus epsilon. Epsilon is some noise, and then it tries to reconstruct X. However, its loss function is X hat minus X, not minus X plus epsilon. So it wants to X hat to be similar to X without noise. Therefore, it can be used for denoising. So it's denoising autoencoder. In overcomplete autoencoder, if you give X rather than X plus epsilon to encoder, it just copies. It doesn't learn anything. It just copies because P is greater than D. Therefore, it can copy each of these to one of the neurons here. It can copy and then it copies back. It doesn't learn anything. Okay. Therefore, for overcomplete, we have to use noise. It will memorize and overfit. Okay. And then metric learning bar. So here, undercomplete reconstruction autoencoder can be used for metric learning actually, and dimensionality reduction if P is much less than D, right? So undercomplete autoencoder can be used for dimensionality reduction because the dimensionality of embedding is much less than dimensionality of input. Okay. If activation functions of all layers is linear, the whole thing collapses into one linear projection, right? So the encoder collapses into one linear projection. The decoder also collapses into one reconstruction. This, if you train it by backpropagation, it gives you PCA. So U becomes exactly the eigenvectors of covariance matrix of data. Why? Can you tell me? Why doesn't, I said it collapses into one linear projection and one linear reconstruction. Why doesn't it converge to FDA? FDA is also a linear method. Why doesn't it converge to some other linear method? Why PCA? If you have watched my PCA in the stochastic machine learning, PCA is the best linear method for reconstruction. It minimizes the reconstruction error. Therefore, when you using backpropagation, you minimize the reconstruction error. It is linear, then it will give you PCA. That's why we add nonlinear activation functions between the layers. Okay. Nonlinear neural network can be seen as an ensemble or concatenation of dimensionality reduction or feature extraction algorithms and kernel methods. Why? In the preliminary lecture, I told you about it. So assume I have several layers of neural network or autoencoder. If the next layer has more number of neurons than the previous layer, it's kernel method because it is increasing the dimensionality. If the next layer has a smaller number of neurons than the previous layer, it's dimensionality reduction. So you can see a neural network as a stack of dimensionality reduction and kernel methods. And we in between of them, we have nonlinear activation functions. So it becomes, overall, it becomes a nonlinear algorithm, and it becomes a monster. That's why deep learning is a monster now in machine learning, because it's it can be seen as an ensemble of algorithms, right? And each layer, interestingly, each layer of network learns its own features from data, its own features, right? Supervised metric learning by supervised loss functions. Various loss functions exist. The supervised loss functions, for example, what do they do? What do they do? When I say supervised, it means that I use labels, right? This is label. So what do? They try to separate classes, of course, in the embedding space. They want to separate classes in the embedding space. The last layer is for classification, right? Assume. So there are several ways I can do it. I can find the embedding space, okay? So as I said, one way is that I use reconstruction autoencoder. In the code layer, I have embedding, right? But so I don't want to use autoencoder, reconstruction autoencoder. I want to use some classes and their labels. How can I find some embedding? The idea is simple. Train a neural network for classifying the classes using cross-entropy loss function and take the one to the last layer embedding. So when you feed xi, what is the last layer? Just the probability of classes, because it's the output of softmax, right? If it is two classes, it will be output of sigmoid. But when we have multiple classes, it's the output of softmax. So the last layer is just for classification, and you do cross entropy on that. It doesn't, you don't care. It's not good for embedding. So use the previous layer, and you call it embedding layer. Embedding layer. Why is it good for embedding? Because exactly in the next layer, it uses the features for classification. Of course, in the embedding layer, the classes must be separated. Otherwise, it would be awful in the classification layer. Right? And yeah, so we take this as embedding. So embedding layer, one to the last. So what do we do? The last, by the way, this backbone network, which is before the embedding layer, can be any network, can be fully connected, can be convolutional, right? And usually the classification layer, which is the last layer, is a fully connected layer. Even if you have CNN at the end, you have one fully connected layer. Okay, so we can use now in this setup, we can use various supervised algorithms, supervised loss functions, right? One of them is cross entropy. One of them is mean squared error. Where is it used? When the labels are continuous, when it is regression, right? So when it please come. Give me a second. What do I do with this? Okay, so one of them is mean squared error. So this is the output of network, and this is the target labels, right? I want them to be similar to each other, and the summation is over the batch, mini batch. However, there is a problem with this. What is that? This is square. This exaggerates the outliers. If you have outliers, the square is poison. Therefore, we can use mean absolute error, right? Which uses L1 norm, absolute value. However, there's a problem with this one. At 0, it's non-differentiable. It's non-smooth. However, it's not a big deal. Why? Because in neural network, they usually calculate derivatives numerically. Do you remember how? I told you once in one of the sessions. They do it numerically. They don't care. Okay? So they don't care about that. I don't know when does this device get tired? So the mean absolute error, as I said, as we do it numerically, it doesn't care. So there are some other loss functions. Let me go through them and then we will be over. So Huber loss, which is a combination of mean squared error and mean absolute error. What does it do? So it will be like this. Do you remember this is L1 norm, which is not as smooth in here. This is L2 norm. This is L2 norm. As you see, L2 norm is like this. Okay. And yeah, I think I was right. Give me a sec. Yes, this is L2 norm. As you see, for outliers, it blows up. L2 norm blows up, but L1 norm doesn't blow up. So let's use the best of the two worlds. So here, for outliers, I use L1 norm, but here, close to 0, I make it similar to L2 norm. So it will be like this. This is called Huber loss. As you see, for close to 0, I use L2 norm, which is a smooth. Otherwise, I use L1 norm. Right? Yeah, another thing is KL divergence loss function. What does it do? KL divergence calculates the difference of two distributions, probability distributions, right? When KL divergence is 0, the two distributions are equal. Okay, it means that all of their moments match. Okay. However, you tell me, how can I use it here? If I use softmax in the classification layer at the last layer, it gives me some probabilities, right? Between 0 and 1. So in perfect world, one of them, the correct neuron should give me 1 and the other one 0, right? So it should be, for example, I have 4 classes and the point that I fed is class 3. So in perfect world, it should be like this, 0, 0, 1, 0. However, when it's not perfectly trained, it gives me something like this, right? For example, then I say to the network, see this as a probability distribution function. Sorry, this is discrete probability mass function, right? Then also the perfect world is this. So minimize the KL divergence between these two, right? You make the distribution what you want. For the next word, the next point, if it is class 2, then the perfect one should be like this, right? So minimize the KL divergence between these two because you are using softmax. Hinge loss is this. Hinge loss is this. If we have 2 classes, C equals 2, yi is -1 or 1, then this is hinge loss. Minimize this summation of m minus yi foxi. So these, but you have this notation. What is this notation? This is maximum of inside and 0. So what does it mean? I want this to be 0. If it becomes negative, I don't care. Okay. If it is positive inside this, if it is positive, then penalize it. If it becomes 0, it's perfect. If it becomes negative, I don't care. Okay, this is a good technique in loss functions. This is called a standard hinge loss. Okay, it's used in triplet loss also. We'll see it in the next session. Okay, M here is the margin. Then let's analyze it. If the signs of the estimated and the true labels are different, what do I mean? If yi foxi is less than 0, the signs are different, right? If the signs of yi and fi of output of network are different, what happens? This is negative, right? Therefore, m minus yi foxi is what? Can you tell me? So this is negative. Therefore, m minus yi foxi is greater than 0. right? Therefore, it can come out of this notation. This should be minimized. So it means that if you are giving me a different sign, penalize it. Penalize it. If their signs are similar, so YIFOXI is greater than 0, therefore M minus YIFOXI, if this is happening, if this is happening, then it becomes negative and you should ignore it. However, if it is greater than M, then if it is 0 and you ignore, and it's done. Did you understand what I'm saying? For this case, when YIFOXI is greater than 0, it means that they have the same sign. Two cases might happen. If FO is greater than M, if FO is less than M. If it is less than M, the loss is positive and should be minimized. If it is greater than M, the loss is 0 and we don't care about it. Okay, this is hinge loss. Hinge loss is used in triplet loss. And the last thing which we talk about in this session is cross entropy loss. Assume we have C classes, so we have C neurons at the end, and if C is greater than 2, then we use softmax activation function. If it is 2, then we can use 1 neuron with sigmoid, right? Then we use cross entropy loss, and this is cross entropy. What do? We use one hot encoded labels YI, right? What do I mean by one hot encoding? This is important. Assume C is 4. Okay, class 1 becomes 0, 0, 0, 1, for example. Class 2 becomes 0, 0, 1, 0. Class 3 becomes 0, 1, 0, 0. Class 4 becomes 1, 0, 0, 0. This is one hot encoded. So I use one hot encoded, and this YIL means the elf element of YI. YI is the one hot encoded, right? L goes from 1 to C. Here C is 4, for example. Okay, and then FOXIL, so elf element of output, right? So basically it means that make the elf element of output of network similar to the elf element of one hot encoded of target. So this is elf element of target, and this is the elf element of output. Elf output neuron. Is it obvious? No? This, assume I have 4 classes. At the end, I have 4 neurons. So assume L is 3 here. This gives me some output. Also, in one hot encoding, if it is class 3, this is 1, the other ones are 0. So I want this to be similar to this. I do it for all of the elements, right? This is exactly cross entropy. Cross entropy makes each element of this similar to each elements of that, the other one, in a one hot encoded version. Okay, so we talked about important loss functions for supervised learning, and as I said, we can use it for learning embedding also. We can use it for classification also. You talked about reconstruction autoencoder. Next session, we'll talk about Siamese networks, are very important networks in deep metric learning. Afterwards, we'll cover variational autoencoder and adversarial autoencoder and GAN. Okay, thank you. Next session, we have midterm next week. Okay, thank you.